Thank you. Thank you. We started working with the two-dimensional objects and the three-dimensional objects before we left on break. They obviously weren't very difficult things. What's really nice about the right geometric, or sorry, I should say, the right geometric solids. You guys remember the right geometric solids? Right geometric solids, if you don't remember, are simply those images that you could, if you think about it, you could stand them up and the base would look just like the top. And of course it's kind of cylindrical type thing where it's vertical. Oh, whoa. I wasn't expecting that at all. So, I mean, some of the best examples are like, if you think about a can, okay, a soda can, bottom looks just like the top, cylindrical. If you think about a triangular prism, let's see if I can do this correctly. So, something like that. That should be that. Okay. You can see that this has a base that's just like the top, and then of course you have the walls, and those walls would be right angles to the bases. That's why it's called a right geometric solid. You understand that? Yes. Any questions on that? I know it's kind of weird. It's kind of tough to draw with the 3D stuff. But everyone okay with that?
Yes.
All right, cool. So, what's really nice about the right geometric solids is that they're so easy to find the volume to them. What you need to do simply is find the area of the base, and this works for all of them. The area of the base. So in this case, we'd be finding the area of a triangle, thank you. And then we would multiply that by how tall that is. So we multiply by the height. You understand that? So if I had, let's say I did have a cylinder, and let's call the radius 2, and we'll say the height is 10. So again, this is a right geometric solid. We call it a cylinder. We find the area of the base, and then multiply by the height. That's simple. So in this case, the base is it's not an oval, it's a circle. So to find the area of a circle, it's pi, radius squared. My radius happens to be 2, so I've got 4 pi there for my base. Questions on that? To find the volume, all I have to do now is multiply by the height, because all I'm doing is stacking those concentric circles right on top of each other. So I'm multiplying by 10. So this would have a volume of 40 pi units cubed. Units cubed. Questions there? Okay.
Wait, no, you said.
I wasn't gonna.
Okay.
Would you normally keep it as pi, or would you like find it all the way out?
I had that question yesterday, and here's my answer to that. The question, guys, was, do I leave it as 40 pi, or do I multiply that by 3.14159, blah, 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 blah. Pi is exact. The symbol pi is the exact number. So in my opinion, I would leave it as pi. For the purpose of my class and in here and working together, I would leave it as pi. Because the more math you do, the more room for error. Okay? Does that make sense? I accidentally put the wrong number in the calculator, and now I got some answer that's wrong. That's fine. When you go on Galileo, they might give you 40 pi, and they might say 40 pi units squared, and you're like, that's the one, and you're wrong. Why? Because it's cubed. And why is it cubed? Anybody know why? Because that's what we've been told. Okay, we'll talk about it in a minute. But the other option that you might see is that they have multiplied it out by pi. So you might see, about 120 something, whatever it is in there. Okay, and then you'll have to know, oh, they went ahead and used pi to multiply that out. And sometimes they'll tell you, use pi as this number. Make sure you use that number. Maybe they'll say pi is 3.14, or they'll be like, oh, use 3.1 or use 3.141. They'll tell you the definition of pi most of the time. If not, then we default to 314, right? Whoop, whoop. Let's talk about why it's units cubed, okay? And it really has to do with how we said earlier. What did I call this first image at the beginning? What type of images? Those are 3D images, right? three-dimensional images? That's the reason, right there. Okay? If we have one dimension, it's called length, correct? So if I said this is 3 centimeters, what's the degree of centimeters? It's 1, isn't it? We don't write it because we understand that. Kind of like if we just have x by itself, we know that the number in front of x is a 1. It's 1x. Now, this is one dimension. When we add a second dimension to that, what are we doing? Aren't we taking this and we're multiplying by whatever dimension is here? So if I take 3 centimeters and I'm multiplying that by 2 centimeters, well, I'm getting 2 times 3, which is 6. But what happens when I take centimeter times centimeter? That becomes centimeters squared because it's 2-dimensional now. Okay? Remember, what's the degree here? It's 1. And when I multiply them, what am I doing with those exponents? I'm adding them. Think about this. If I did a times a, what is a times a? A squared. Okay? Units of measurement, very much like a variable. So when we have a third dimension, in this case, we're going to be multiplying by another here. Did I call that 2 again? It was a 4, just kidding. So if I did 4 centimeters, then I've got 3 times 2 times 4, making that 24. Okay? Centimeters times centimeters times centimeters would give me centimeters cubed. 3 dimensions, 3D, so the degree should be 3 on centimeters. Make sense? Awesome, awesome. Okay. And again, write geometric solid, so you find the area of the base, multiply by the height, and you get to go. Super simple. Okay? Now, there's something else I want to show you. Well, actually, it's one thing that I need to teach you, which you probably haven't seen before, but this is called Cavalieri's principle. Okay? And it's kind of like, it's pretty mind-blowing. It's really cool. I like it. I'm going to try to see if I can do this well. I always mess things up. But, that look decent? This is where I mess it up right here. Let me see if I can, oh, you know what? I'll use it the same. I'm cheating here. I didn't think about this yesterday. What? God can't help you now. JK. Cool. Close enough? So, I've got two geometric solids here. One is definitely a cylinder, and the other one is like a cylinder that's twisted, huh? Kind of like it was cut in an angle type thing. So, when the question was asked to us first, like, all right, which of these has more volume? I'm like, well, the slanted one's going to have more volume, right? No? And what do you think? What's your opinion? Like, here was my my idea. Was, all right, you know what? These are the same, this is a height, right? If I think about triangles, if I did this and I twisted this, wouldn't this kind of like take a little dip and it making this longer, which makes it have more area? That was my idea. It doesn't make sense, Rocky Tototan? No? So which one has more area? Or I'm sorry, more volume? You don't know? They're the same? Why would you think they're the same? But what? How would you find the volume of that?
Same thing.
How?
Same.
Did you guys watch my video already? Shame on y'all.
Wait, what do you mean by like cutting it like that way to the angle?
Is it like slanted like other bottom?
Okay, yeah, so my bad. There's a little bit of information missing. So let's say these are both sitting on a plane. Okay, so they're both sitting on the same plane at the very bottom. So they have the same base. So it's like I sat them both on the floor. And there's also a plane up here that exists that they both touch at the top. Okay, so the bottoms are the same and the tops are the same, so they both have the same height. So the height of this bad boy, we'll call it H, would also be the height of this bad boy. Okay, so they're both just the same height. Did that help a little bit more? Okay, so the question still continues, which has more volume?
Well, then wouldn't it be the same volume?
But they're the same height, and one's twisted a little bit. Now, Matthew, you're not wrong. You're right. And that's what Cavalier's principle says, is if you have an image like this that's been kind of slanted a bit, it's still going to have the same volume as the other piece. And the idea is this. And I think I'm just going to jump to the visual because it makes more sense. And hopefully you guys can see, so you're going to probably have to move around a little bit. It just kind of came to me because some people wouldn't get it. Okay, so here, let's see here. I'm going to make 2 stacks of pennies. Which of these pennies has more volume than the other? Which penny would have more volume? Don't they all have the same? Aren't they all just made by a machine, so they're all the same? So here's what Cavalier principle is saying. Try to make two equal stacks now. That's changed. Yesterday I got it perfect. It was kind of like witchcraft. I was like, wow, I'm amazing. No, the other one's shorter. Okay, cool. So can everyone see those 2 stacks of pennies okay? Okay. So here's the idea. Obviously these two would have the same volume, correct? The one on one side would have the same volume as the one on the other side. Now if I took a cross section, one of the pennies from the inside, and I took the same penny from the other side, right in the middle, which of those two would have the same volume? Or sorry, which of these would have more volume? Neither, they would have the same, right? So what I did is I took the same cross section. So what I did is I took the penny that lives right here, right in that spot, I took it out, okay? Now, if I took out the same penny over on this side, okay, the question is which of those two would have more volume? And of course the answer is it's the same. Neither one does, right? So Cavalier's principle says, well, you know what? If you could do that for every single one of those and match it up here, take this one here and match it up with this one here, and just go across this whole cylinder and do the same thing over here, then every single one would have a corresponding cross-section on the other one, wouldn't it? Kind of like these pennies do over here. For every penny that I've got on one side, I have a corresponding penny on the other side, correct? But if I take this one over here and I slant it a little bit, you can't do too much on these, okay? It's still the same idea. So even though one might be slanted, okay, it might be slanted, it would still have the same volume as the other one. So Cavalier's principle is pretty kick butt that way because when you think about it, it's like, oh man, how am I going to find the volume of that bad boy? Well, you'd find the volume of this the same way you find the volume of this. Area of the base multiplied by the height. Because remember when I talked to you guys, Matthew?
So you said the corresponding, if you took one out.
The cross sections?
Yeah.
Mhm.
What if you mixed it up a little bit? Like,
Well, that's the idea behind Cavaliers, to prove that you can find the volume of this the same way that you find the volume of this. Because all he's doing is, instead of stacking them straight up and down in a right angle, they're kind of slanting a little bit. Now remember, these have a little bit of girth, don't they? They have some thickness to them. But if they were completely flat, as a 2-dimensional circle would be, okay, because that's technically what this idea is, and then I'm just stacking those 1-dimensional circles all the way across. So what they're saying is, if you want to find the volume of this bad boy, and he happens to have a radius of 3 and a height of 5, then this would be 9 pi for the base multiplied by the height of 5. So the volume would be 45 pi units cubed. And this one over here, if this had a radius of 3 and a height of 5, what would its volume be? Same thing. Okay? So according to Cavalier's principle, as long as it has that height and you can find the base, you can find the whole volume. Question on Cavalier's? No? It's not really a difficult idea. All they're doing is taking all those little slices and they're tilting them a little bit, but it's still the same number of slices, correct? Whole beans. So, what I want to do today is I want to practice some of these because the idea is the same for every single one of them. If you understand how to find volume, you can find the volume for anything, right? So, let's go out to the lobby. Let's go out to the lobby. I want to find my camera tool. Okay, cool. So let's take a look at some of these here real quick. Any one of these you guys would find kind of particularly interesting that you would like to find the volume of?
10. 7.
I heard 10 first, so let's go ahead and grab 10. I'm going to copy this bad boy. Actually, can we start with a non-pyramid?
Yeah.
Can we start with one of the other ones? Which one? 4?
4. Yeah.
Okay, that's definitely a right geometric solid, yeah?
Yeah.
Super easy. Yeah. Okay, so here's my right geometric solid. How do I find the volume of a right geometric solid? Area of the base
Times the height.
multiplied by the height. So in this case, my base is a, what is that, a pentagon? So I just want to show you the base. Yeah. Okay. So here's my base because I need to find the area of that first. Let's see here. What do I know about this? I know that from the center down is 5.5. What else do I know? Anything else? Okay. Make sure that you examine the whole thing. Do you guys see this 8 up here? What's that telling me?
The side.
That's one of the lengths of the sides. Would it be any different in the bottom? No, because they're right geometric solids, right? That means the bottom would be exactly as the top. So that means that the length here is 8. Oh, well, you know what? Isn't this technically a triangle? If I did that? So I can find the area of that triangle. Base times height divided by 2. Correct? See, 8 divided by 2 is 4. 4 5s is 20. And then half of 4 is 2, so 22 centimeters squared. Can someone check that for me? Someone just give me a thumbs up there. The area of that triangle is 22 centimeters squared. No? No thumbs up? One thumbs up? I need another one. Thank you. So that gives me the area of the base, right? All I need to do is multiply by the height now. What is 22 centimeters squared?
Just that.
It's the area of this triangle. How many of these triangles do I have? I got 5 of them. See that? 1, 2, 3, 4, 5. So what do I do with 22? Multiply by 5. 5 20s is 100. And then 5 times 2 is 10, so it's $1.10. Someone confirm that for me?
Yes.
Okay, so now I've got the area of the base, right? Now I have to just multiply by
The height.
the height. And how high is it? So yeah, because there's 10 of these bad boys. So that's 10. Oh, this is in yards. I was putting centimeters. JK. Yards squared. Yards squared. Yards. So 110 times 10 is going to be that. And then what's yards squared times yards?
Yards cubed.
Yards cubed. So there's my volume. The volume of this right geometric pentagonal prism. Questions there? What's up?
I like how I got lost. Like, why did you do 8 times 5?
It was in this red. Let me see if I can get rid of this. Yay, go away. What we did is we tried to find the area of the base, right? Because to find the volume of this, all I got to do is find the area of the base, multiply by how tall it is. Make sense? So here's the image of the base. We found that this piece is 5.5. And from the top, I can see that the side lengths are 8, which means this is 8. Well, what shape is this? It's a triangle. How do I find the area of a triangle? Base times height. Then that's where this came in. Now, the area of one triangle was 22. But how many were there? 5. So that's where 1/10 came from. We're good? Thank you for asking.
Just have a question on the penny things.
On what?
The penny.
What about my pennies? You
Okay,
can't have
you know how, okay, my question was like, if you take a penny out from the straight cylinder,
Mhm.
and then you take one out from the slanted one from the top, instead of taking it from the bottom like it was, would that make a difference?
Cavaliers principle doesn't say do one from the middle, one from top or bottom. You have to do the exact same cross section.
Okay.
It has to be the exact same cross section. So this one. I mean, ideally we know that you could probably mix and match them.
Yeah.
But what he's saying is, you know what, and kind of to prove it without really having to go too deep, is we're cutting the same cross section. So I'm going straight across and swat. And I got these two slices. Those two areas would be exactly the same. And if I could do that for every single one of these unit circles that are in here, then the volume of all those circles added is the same as the volume of all of these circles added.
Yeah.
Okay?
Thank you.
Cool beans. Are we good here? Can we move on? Yeah. Okay. Let's do one more right geometric solid. Pick it. Which one do you guys want to do? That's not a right geometric solid. That's a pyramid. 9? That's a cone. That's still pyramid. Okay. Well, 7's just like last one. You guys want to see 7?
6.
6?
No, do 6. Yeah.
You guys don't want to see the cheese?
6. Just
Yeah,
6.
Let's do the cheese real quick, and then we can do one of the other ones. Cheese. Okay, so here's my cheese. Oh, cool. The answers are there, so we can check our work. Okay, so again, area of the base multiplied by the height. That's simple. In this case, what shape is our base? Triangle. Oh, it's a right triangle. That's even cooler because that means that I could call this the base and that the height, correct? Everyone cool with that?
Yeah.
So 6 times 8 divided by 2, that's a 3, so 24 kilometers squared is the base. And what do I multiply that by?
By 3.
By 3. Because remember, the base is going to be the one that has top and bottom be the same, which means this is the height of 3 kilometers. 3/24 is 60, 72.
Yeah.
And then kilometers squared times kilometers is going to give me kilometers cubed. Taco Bell snack wrap. We get to go. I didn't like it. I didn't like the Taco Bell. I bought one because I want to tell the guy I'm good to go. You know, so I need to do that, and then I did it. But then when I ate it, I was like, it's not good to go. Gross.
Did you get the spicy nacho one?
I just said, let me get a Taco Bell snack wrap.
Oh, then you probably got the beef and potatoes.
No, there was no potatoes in it. But it was Brody. I still love their Father burrito though. But I hate when they do that. You guys ever ordered the Father burrito at Taco Bell?
No.
I hate when they put like all the cheese on one side of the burrito, like the bottom half, and you get all the beans on the top half. It's not evenly distributed. It's like, man, nobody asked for a half and half.
You get a mouthful of one or the other.
Yeah, it just makes me mad. Now my favorite thing though at Taco Bell has to be the enchilada. Do they still sell that in there? The enchilada's bomb, huh? Yep. Taco Bell's just gross. I don't know why they even sell it, but it's so bad. It's so good. It's like McDonald's.
It's not good for you. Like
They got rid of their dollar menu.
Oh, they always do.
Why? They got rid of the dollar
No more
menu?
hot.
Yeah, you can get hot spicy for $1.
I was gonna say, I was really upset. They're like, well, they don't have a dollar menu.
Taco Bell or McDonald's? You can still get the spicy for $1.
You can?
Yeah, they have a handful. It's like 3 or 4 items. As a need or what? Okay, thank you. Thank you. So, alright, we did a few right geometric solids. Pretty simple thing, right? Find the area of the base, multiply by the height, and you're good to go. So let's take a look at one of the other ones. And some people were asking me for 10. So let's take a look at 10 then. Okay, So here's 10. Okay. Now, do you guys remember my axiom, my informal proof of why we did the cone? Do you guys remember when we did the cone? And I said to you, hey, you know what? When I did the cone, I said, you know what? Imagine that this came from a cylinder, right? And what they did was, oh, that's horrible. that's just bad. Yeah, do you guys remember that? Imagine that that's your cylinder just standing up. And if I looked at the shape of that bad boy, it'd be like a triangle, wouldn't it? And this is what I'm looking for, which is one of how many pieces? 3. So I said, oh, that's going to be 1/3 of the cylinder, which was area of the base times the height. You guys remember that? Guess what? Same thing for all pyramid-looking things. It's just 1/3 of it. Okay? So if I'm going to do this problem right, then I'm going to pretend that this was a right geometric solid with a pentagon base. So I'm going to find the area of the base. So let's go, where? So the base is a pentagon. Yeah? Let's see here. They gave me this here, did they?
Yeah.
What is it? Oh, there we go, the little arrow, thank you. So I've got that, which is 8.3. And I have the side length, don't I, which is 12. So I can say, oh, you know what? If I did this, that's a triangle. So my base would be 12 times the height of 8.3, and I'd have to divide that by 2, because that's a triangle, isn't it? So 12 can divide by 2, that'd be 6. So 6 times 8.3.
49.
Thank you. 49.8 centimeters meters squared. Okay? And then there's 5 of those? Correct? Yes or no?
Yeah.
Cool. So we're going to have to multiply that by 5. So that's 50 times 5. That's 250 minus, so 249?
Yeah.
Yeah?
I wasn't listening.
Yeah, it's a 49.
Woo! Go rounding skills. So that's 249.
Wait, what's
Times
11
the
meters on that?
Oh,
Times the height.
that's a great question. What is 11 meters? Well, isn't that the base? And that's the very top of it, isn't it? AKA height? Which is what we need, isn't it? Because we need to take this bad boy, multiply it by the 11 meters high. So what's 249 meters squared times 11 meters?
Wait. 2,739.
Wait, what?
That doesn't match.
Is that the answer?
What does it match that?
Okay. What did we just find the volume of? We found the volume of the right geometric solid, the whole thing. Is it the whole right geometric prism?
1/3.
It's 1/3 of it, isn't it? So what do we need to do? Divide this by 3. Or multiply it by 1/3. I'm just going to divide it by 3. It's easier. And tell me what you get.
913.
Oh my God!
913.
Beautiful. Beautiful.
Is it the reciprocal if you did it? Like,
It's the same thing.
right?
You can even go that number times 0.333333333 until your finger gets tired. Hit enter and you're going to get 913. Do it.
Okay, so wait, what's this thing called? You said they're all triangles.
All cone looking things, yeah. So let me tell you what I mean here. Starting from the top, this would be 1/3 area of the base times height because it's kind of pyramid shaped. This would just be area of the base times height. This one?
Wait,
Yeah?
can you go back to the other one? Because I didn't know how you got 5.
Here?
Yeah.
How did I get 5?
Because there's
Because there's five.
Yeah, this number is the area of this triangle, isn't it? But there's how many of them? Yeah, so 1, 2, 3, 4, 5. That's where it came from. Huh? Exactly like the one before. For sure. What's up? I know, and that's what we kind of talked about last. You weren't here for that, but here's kind of my informal proof for that. This is what makes the most sense to people. Okay, no matter what the shape looks like, if it's going to be at a point like this, kind of like a pyramid. If I look at it at any right geometric prism, from straight on, it's going to look like this, isn't it? Okay, whether it's a cone, whether it's a pyramid, no matter what. Now, it's also going to do this, isn't it? Okay. So, my formal proof is, think about this. What you got here is, you want this piece of it, which is one of 3 pieces. Because I'm cutting this away, I'm cutting that away. Now, people will say, oh, well, that's not exactly it, is it? But think about this. Isn't there also a gap in the front of this? And a gap in the back? So this piece with the front is actually a third of it. And this piece with the back gap is the other third. And then your cone in the middle would make the 1/3 as well. That make sense? Good. Yeah, so if you look at it from the top, no, it wouldn't be a very good visual.
Yeah.
Thank you. What's up?
So on the other side.
This right, huh?
Yeah.
We didn't do that one right now.
The one we just did.
Where'd it go? Here?
It's number
Is this it?
Slide
No,
eight.
it's number 8.
Slide 8.
Oh. Yeah, what about it?
How did you get 2?
I don't know. Hold on.
Oh, that's.
Oh, this is from the triangle. This one right here? Is that what you're talking about? Well, what shape is this? How do you find the area of a triangle? Right? So base is 12. There's my 12. The height was 8.3 divided by 2. Okay, this is the one triangle. And then what I did was, because there was 5 of them, I multiplied it by 5. That gave me the whole area of the base. Then I multiplied it by the height, which was 11 meters. And then because it's cone shaped, I only need a third of it. So I divide by 3. Okay. Do you believe my informal proof? Do you believe my axiom?
Oh yeah.
You guys remember, right? Axiom is a way of proving something without really proving it. But it makes sense, huh? I love axioms. Alright, cool. So, what I was doing, I was kind of going through these, and I was saying, let's see if you can think about which formula you would use. If we start with this, number 2 here, how do you find the volume of this? It's like a block. You just take the area of the base, multiply by the height. Here, area of the base, multiply by the height. Area of the base, multiply by the height. Area of the base, multiply by the height. Area of the base, multiply by the height, but I only need 1/3 of it. Area of the base times the height, but I only need a third of it. Okay? So every cone, all I need, treat them the same way as these, but at the end, you just need 1/3. And that's it. That's all of them.
How about the circle?
So that's every.
Oh, circles are different. I mean, obviously, they're not right geometric solids at all, right? Now these, you should have the formula. You should have your formula. Oh, there it is. So let's do that real quick. We'll take this one right here. Now these are so difficult. Oh my God. 4/3 pi r cubed. That is your formula. 4/3 pi r cubed. Remember we watched that whole video thing?
Yep.
Okay? So I take the radius, which happens to be 5, and I cube it. Okay? Now for those of you guys that are kind of intimidated by fractions, this is really this. It's really that. Okay? It's 4 times pi times the radius cubed, all divided by 3. Oh my god, that's cool. Also just a third. So we're going to get 4/3 pi times 125. Is that correct? And then 4 times 1. Oh, I don't want that. I don't like that at all. I don't do that no more. So 4 times 125. That's 400. That's 500 pi thirds. Now, if you want to sit there and actually do it, that's fine. But I can already tell you this is going to be about 510 or something like that, because 3 and pi almost cancel each other out. So you get a little bit more than 500.
Gives you the answer.
Yeah, 523. So that gives you a good idea of where you're supposed to be. But what's that?
Read that 1.5.
5 times 5 times 5.
You're pressing enter on.
Steer it up, little darling. Steer it up. I gotta stop singing because then I hear myself on the recording. I'm like, man, I got a horrible voice and nobody tells me anything.
When you were taking
Thanks, Felice.
when we were taking our last Galileo, you kept whistling and I got stuck in my head for like 2 weeks.
Give her
It's about.
Questions on these? Any questions whatsoever? This is so difficult. So looking at these, anything that you want to do in here? Anything else seem kind of a little bit off? Like you're not sure maybe? Alright, cool. That's a cylinder. So area of the base times the height. So the radius is 3. That'd be 3 squared, which is 9. 9 pi. 9 pi times 4. 36 pi. And I'm done. Okay? Sweet.